Good day, everyone. Welcome to Tagum City National High School Science Web Course on Quarter 2 on Force, Motion, and Energy. In this video, we will be discussing the images formed by mirrors and lenses. We will also be talking about the different characteristics of images formed by mirrors and lenses. A great deal of evidence suggests that light travels in straight lines under a variety of circumstances. For our convenience, this beam of light will be called a ray. Although light rays leave the object in many different directions, normally only a small bundle of these rays can enter the observer's eye, as shown in the image on the right. If the person's head moved to one side, a different bundle of rays will enter the eye from the object. When light strikes the surface of an object, some of the light is reflected. The rest can be absorbed by the object, somehow being transformed to thermal energy, or if the object is transparent like glass or water, part of it can be transmitted through. This illustration shows how an image is formed by a plane mirror according to the ray model. The rays are shown reflecting from the front surface. Rays from two different points on an object, which is the bottle on the left in the picture, are shown. Two rays are shown leaving from a point on the top of the bottle and two more from a point on the bottom. Rays leave each point on the object going in many directions, but only those that enclose the bundle of rays that enter the eye from each of the 2 points are shown. Each set of diverging rays that reflect from the mirror and enter the eye appear to come from a single point behind the object or behind the mirror. This point, which we call the image point, shown here by the dashed lines. The point from which each bundle of rays seem to come is one point on the image. For each point on the object, there is a corresponding image point. When you look straight into a mirror, you see what appears to be yourself, as well as various objects around and behind you. Your face and the other objects look as if they are in front of you at the back of the mirror. But what you see in the mirror is an image of the objects, including yourself, that are in front of the mirror. Also, you don't see yourself as others see you, because left and right appear reversed in the image. But how does this image form in a plane mirror? The image appears as far behind the mirror as the object is in front. The image distance equals the object distance. From the geometry, we also can see that the height of the image is the same as that of the object. The light rays do not actually pass through the image location itself. The image would not appear on paper or film whenever one is placed at the location of the image. Therefore, it is called a virtual image. This is to distinguish it from real images in which the light does not pass through the image and which therefore could appear on a white surface or on film or on an electronic sensor placed at the image position. Our eyes can see both real and virtual images as long as diverging rays enter our pupils. We will see that curved mirrors and lenses can form real images as well as virtual images. A movie projector lens, for example, produces a real image that is invisible on the screen. Now, let us look into the images formed by curved mirrors. A spherical mirror is called convex if the reflection takes place on the outer surface of the spherical shape, so that the sphere or the center of the mirror surface bulges outward the viewer. Convex mirrors are sometimes used on cars and trucks for the rear view mirrors and in shops to watch for theft because they take in a wide field of view. A mirror is called concave if the reflecting surface is on the inner surface of the sphere, so that the mirror surface curves away from the viewer. Concave mirrors are used as shaving or cosmetic mirrors, and those magnifying mirrors because they do magnify. To see how spherical mirrors form images, we first consider an object that is very far from a concave mirror. For a distant object, the rays from each point on the object will strike the mirror will be nearly parallel. For an object infinitely far away, like the sun and stars, the rays would be precisely parallel. These rays will cross each other at very nearly a single point, which we call the focus. As shown in the diagram, the incoming rays are parallel to the principal axis, which is defined as the straight line perpendicular to the curved surface at its center. The point F, where incident parallel rays come to a focus after reflection, is called the focal point of the mirror. The distance between F, that's the focal point, and the center of the mirror is called the focal length, or the small letter f of the mirror. The focal length is half the radius of the curvature, or the C. The point C is the center of curvature of the mirror. It is also the center of the sphere of which the mirror is a part. Now let us determine where the image will be formed for a given point at the top of the object by finding the point where rays drawn from the tip of the arrows converge after reflecting from the mirror. To do this, we can draw several rays and make sure these reflect from the mirror such that the angle of reflection equals the angle of incidence. There are three statements here that we will be following. One is that ray 1 goes out from object parallel to the axis and reflects through F. Ray 2 goes through F, that's the focus, and then reflects back parallel to the principal axis. Ray number 3 is perpendicular to the mirror and so must reflect back on itself and go through C, which is called the center of curvature. All three rays leave a single point on the object, and after reflection from a mirror, the point at which these rays cross is the image point. All other rays from the same object point will also pass through this image point. To find the image point for any object point, only these three rays need to be drawn. Now let us apply the ray diagram in determining the image formed by a concave mirror. Suppose we have a concave mirror with an object placed beyond the center of curvature. Where would the image be formed? Of the three rays used in the diagram, only two of these rays are needed, but the third serves as a check. Let us begin the ray diagram by drawing the first ray. Remember that ray 1 goes out from object parallel to the principal axis and reflects through F. Next is the second ray. Ray number 2 goes through F and then reflects back parallel to the axis. And lastly, the third ray, ray number 3, is perpendicular to the mirror and so must reflect back on itself and go through the center of curvature. Now, looking at the intersection point of the three reflected rays, which we have illustrated as dashed lines. This intersection point is where the image forms. So a complete image of the object is formed because the light actually passes through the image. This is a real image, which will appear on a white surface or a film whenever one is placed there. This can be compared to the virtual image formed by a plane mirror where the light does not pass through that image. The analysis for concave mirrors can be applied also to convex mirrors. However, the reflected rays diverge but seem to come from a point F behind the mirror. This is the focal point, and its distance from the center of the mirror is the focal length. This time, let us perform a ray diagram for an object placed before a convex mirror. Consider the following illustration. Where would the image be formed in a convex mirror? Using the three different rays on the previous example, we will be able to determine the image. So ray 1 goes out from the object parallel to the axis and diverges through F. Next is a second ray in which ray 2 goes through F and then reflects back parallel to the axis. And lastly, the third ray, ray 3, must go through the center of curvature, which reflects back to the object. If we have noticed the divergence of the reflected rays from each other, they cannot form a specific image. However, if we are going to extend a virtual ray beyond the mirror, an intersection might be formed by these extended virtual rays. This is the reason why convex mirrors form virtual images. Using the ray diagram, we will now be able to predict and characterize the images formed by curved mirrors. There are several characteristics of images, which are defined by the following: the type of image, the location of the image, size of the image, and orientation of the image. There are two types of images. One we call the real image, which was already explained. Second, we call it the virtual image, which was also explained in the previous sections. We can also characterize the location of the image formed in a mirror through the following: before the focus or the F, on the focus or the F, between the focus and the center of curvature, on the center of curvature, and beyond the center of curvature or the C. Images formed by mirrors may also be characterized by size. Some images may be smaller than the object or same size as the object, or even larger than the object. Lastly, images may be inverted or upright, which characterizes its orientation. Now, using the previous examples, let us characterize the image formed by a concave mirror with an object placed beyond the center of curvature. Let us perform the ray diagram and draw the image. So, the location of the image would be between F and C. Its size is smaller than the object. Its orientation is inverted. And the type of image is a real image. Using again the previous example, let us characterize the image formed by a convex mirror with an object placed before it. Let's perform the ray diagram and draw this image. So the location of the image would be before F, or that's before the focus. Its size will be or is smaller than the object. Its orientation is upright, and it is a virtual image. So there you have it. We have applied ray diagramming in predicting and characterizing the images formed by mirrors, especially curved mirrors. On the next video, we will apply mathematical concepts such as mirror equation and magnification equation to quantify the qualitative characteristics. See you next time.